Okay, so this video is going to cover the topic of contour lines from the appendix to chapter 1. This is also, we're going to use this in chapter 2 when we're going to talk about indifference curves of a utility function. We're not quite there yet, so we're just going to talk about contour lines in general. Now, contour lines are relevant, and we use this when we were talking about functions of two or more variables. Contour lines are also referred to in math as a level curve of a function. So what we have here is a function of function f and y, and so the value of that function, we'll say that's going to be variable z. So we have two variables that go into the function, x and y. And this is the function we're actually going to get the contour lines for. So it's going to be 2 times x times y. And graphically, when we come over here, and how we're going to use this for indifference curves is that we're going to have the variables x and y on the two axes. And that's nice because this gives a two-dimensional graph. Well, we know there's a third variable z. If we wanted to graph this function the way we would do it normally, a function that's y is a function of x, well, we'd have to put z in here too. So that would give us a third axis here, a third dimension. And then we would be graphing it in 3 dimensions. Well, 3-dimensional graphs are kind of tricky. They're not very, many people don't find them very helpful. 2-dimensional graphs with just an x and y here are quite helpful. So what we can do is we don't have a z here when we just have 2 axes. Well, we just have x and y, and then what we're going to graph here in our 2-dimensional graph is all the values of x and y that would give us a certain level of z. And this is why it's also referred to as a level as a level curve. A contour line would come from a map. If you've ever seen a map with that, which will show like, oh, here's the elevation 500 line on the map, and the cartographers, the map makers, would draw, in effect, everywhere on this map that the elevation is exactly 500 feet. And so that would be giving you a sense of, well, the areas that's where the elevation is greater than, you're sort of like graphing, mapping out a hill in that regard. So this is the same idea of a contour line that you might be familiar with from a graph. And it's going to be for a function of 2 variables. Again, we'll take this specific thing. So how do we go about to do a contour line in this case? What you would do is you pick some number that you want to set this function equal to, because we're going to essentially solve for all the values of x and y that make this function 2x times y equal to some specific number. So I'll just pick here because it's a nice number. Let's pick 20. So we're going to set a value of z for 20. And so then what we're going to have as an equation here, 2x times y equal to 20. We want to find all the different values of x and y that would make this function have a value of exactly 20. So, and what we're going to do is we're going to write some numbers down here, and then we're going to graph them, because we're going to write the numbers here, and then we'll graph them over here. So, what you can do here is just very sort of arbitrarily pick a number for x and then figure out what y would have to be. So 1's a good place to start. So you say, if x was 1, what value would we need to have for y to get a value of 20 when we out of this function? So you have 2 times 1 times y. So you have 2y is equal to 20. And when you divide by 2, you get that, well, y would have to be 10. So if x was 1, y would have to be 10. Now, if you're familiar with like sort of the symmetry of a function like this, then we can sort of say like, oh, if y was 1, then x would have to be 10. Let's pick if x was 2. If x was 2, we have 2 times y equal to 20. So 2 times 2 times y, that would be 4y is equal to 20. And then that would give us, so you divide through by the 4, that would give us that y would have to be 5. And again, that would also give us that if x was 5, then y would be 2. And then let's see if we, what else can we take? Oh, we could take, we've got a couple numbers here. That looks like it'll be enough. So the point of doing this is to try to get some numbers, and then you're going to come over here and graph them. And what you want to do is to be able to get a good sense of what shape this level curve is going to have over here, or this contour line. So we come over here, we're essentially picking these numbers, and we have to graph them. So with 1 and 10 would be on here. So if x was 1, we know that y could be 10. So that gives a point there. And if y was 1, x would be 10. That would give us a point there. And then we also know we've got 2 and 5. So if x was 2, we know that y would have to be 5. That would be right here. And if y was 2, x would be 5. That would give us a point right there. And, well, that's enough for me to be able to sort of see like what we have to have. If you're at a point where you're not sure yet what the shape is going to look to be, then you'd want to graph. You don't want to plug some more numbers in here for x, and then figure out other values for y until you get enough. That you could get a sense of what it's going to look like. So in this case, the level curve is going to look something like this. I missed the point there. And we would refer to this as the z equal to 20 level curve. It's the level curve or the contour line for this function of two variables, where the value of z is the output of the function here, where the value of the function is 20. And all of the different points, all the different combinations of x and y here would be combinations of x and y that would give us a z value of 20. This ends up being kind of nice because now in 2 dimensions, we can get something that would give us something about the shape of this function. If you want to think about it in terms of a map, if this would be sort of like saying if you're thinking back to elevations, which was what you'd have for contour lines on a map, it's like, oh well, this would be the elevation 20 line, and then if you've got other lines in here showing other elevations, that gives you then a good sense of like, oh, where there are hills or mountains and where there are valleys and so forth. And we're going to use this for the same thing. We get this for indifference curves. We'll come back to that in chapter 2. But this is just the issue of coming up with like what is a contour line, how it applies for a function of two variables. And again, to preview it, this is something we will use in chapter 2 when we get to indifference curves. Okay, so that's contour lines.